Hello and welcome back to part 6 of this YouTube video series on Introduction to Convolutional Neural Networks. In the previous part, I basically implemented convolutions and max pooling using nested for loops in Python, and we saw some of the formulae for carrying out convolutions as well as max pooling. In this particular part, I'll be building upon that, taking our example again. And I'll be basically discussing backpropagation, different steps of those, carrying out derivatives, and applying chain rule to actually come up with a working piece of equations that will be easy to actually implement in Python to carry out backpropagation. So let's dive in and see our example again and build the backpropagation framework for that example. So before discussing this backpropagation in detail, let's go to our original example back. We have a 32 by 32 image. We have two kernels, K1 and K2. Let me call it K2. And their convolutions are C1 and C2, and then we apply max pooling, and we have S1 and S2. Both are 16 by 16, and then we flatten them out to a long thin vector. Let me call that vector as F. And then we have a softmax unit, softmax layer with 5 units, and that's a fully connected layer. And we basically have this basic structure, and the loss function we are using is right now is a squared loss function. So let's discuss some of the details here for this particular example. Let's first count the total number of parameters for this whole network. So we have 5 parameters for this particular filter. So 25 parameters, 5 into 5. So we have 25 parameters for this filter plus 1 bias parameter. So plus 1. Then we have again 26 parameters for K2. So plus 26 parameters for K2, again 25 parameters for the filter, and 1 parameter for the bias term. Then we have basically no parameter for max pool layer. There is no trainable parameter here. And then we have basically a long thin vector, which is, so let me go to the next slide. We have 26 parameters for K1, 26 parameters for K2, and then we have a vector F. Vector F whose size is basically 16 square plus 16 square, which is, so 16 square is 256, 16 square plus 16 square is 512. So that vector is basically 512 by 1. So, and then we have 5 units. So unit 1, unit 2, unit 3, unit 4, unit 5. Each unit has its own bias. Let's say B1, B2, B3, B4, B5. So this particular unit has a total number of parameters. If that's a fully connected layer, all these numbers, 512 numbers, they are connected to this. And the weight for this is, vector for this particular unit has 512 parameters plus 1 parameter, which is the bias parameter. And we have 5 such units. So we have 5 times 5, 13, because 1 for the bias. So these are the total number of parameters for this particular example that we are working with. And what we basically are interested in is to compute the, if we represent this weight matrix, if we represent this as a weight matrix, and then the weight matrix will be, let me represent the weight matrix as 5 by 512, and this F already as a vector, which is 512 plus, let's say we represent this capital B that contains all the biases, which is 5 by 1. So this is the transformation that actually we do, and let's say this is a softmax unit. So we apply a logistic sigmoid on that, and that gives us a result, which is y hat, which is again a 5 by 1 vector. And our loss basically is y hat minus y let's say we sum that for all indices and take their square. For all indices, I varies from 1 to 5, and this is just a constant term 2. And our goal is to find out the derivative with respect to W to update W. And then our goal is to find out the derivative with respect to each of these biases to update these parameters. And then our goal is eventually to find out the derivative with respect to all the parameters of K1, the derivative with respect to all the parameters of K2 to update these parameters for gradient descent. And then we have to find out the derivative with respect to this bias and derivative with respect to this bias. So basically, to update parameters in stochastic gradient descent or batch gradient descent or whatever, we have to find out we have to differentiate our loss with respect to those parameters to update those parameters. So how to actually find out these derivatives in this kind of complicated scenario? So let's take an example, and before that example, we already have found this total number of parameters in previous slide. So let me move on to the chain rule. If you see, for example, this is our loss, this is our loss, and that is a unit that actually producing, let's say, y hat 1. And for this particular unit, there is a vector f, which is 512 by 1. And then there is, for example, let me think about this softmax layer having all these units. And then we have a W matrix inside that actually takes this, and we want to compute the loss. Now, if we want to find out the derivative of L, the loss function, with respect to W, we want to differentiate, we want to find out derivative of L, the loss, with respect to W. All we want to know that the changes in W contributes to what changes in L. So for example, what is the impact on L? What is the impact of changes in W? What is the impact of those changes on L? And that impact can be computed as the impact that the changes in W, creates over y hat, and then the impact that those changes in y hat they bring over to L. So this particular formula is called chain rule, and this is very, very handy. If you see in this particular case, if you want to see the contribution of W to L, that is the same as how W contribute to Y, and then in turn how that Y contributes to L. And this is the chain rule, and this forms basically the basics of all the derivatives that we will be computing, and the things will become very layer-wise, kind of component-wise easy, rather than to think about. So for example, if you think about this network, we also have to find out the derivative of the loss function, which is at the very end with respect to K1. So now there are a lot of things inside, and we want to move to, we want to differentiate it with respect to all the parameters of K1. But what happens is we basically, due to the chain rule, the gradient will be back propagated to this layer, and K1, the impact of K1 will be shown onto, for example, C1, and then impact of C1 will already be computed on. So this actually chain rule simplifies a lot of this detail. So let me go to actually compute these derivatives. So for example, let me describe this differentiation of this loss with respect to a particular parameter, let's say I comma j. Remember, in our example, our W is 5 by 512. So what is the derivative with respect to this particular entry of this matrix? That's a matrix. For example, if the value of I is 2 and the value of j is 5, I want to know what is the derivative with respect to this particular parameter. And that you can see by chain rule, that is basically the derivative of the loss with respect to the ith unit at ith logistic unit in the softmax layer into, by chain rule, what is the impact that this particular parameter generates on this y hat. And if you see, this particular thing is really simple. I mean, what is the derivative of and if you see the differentiation of the loss with respect to yi, if I just rewrite the loss function, our loss function was summation I varies from 1 to 5, 1 over 2 y hat I minus yi, where this yi is the target variable, the target, and that is available with the data, and that's the loss function. If you compute the derivative of this loss function with respect to yi, you can notice this simply brings this result, yi. That's it. So that's the derivative with respect to that. And now next is, what is the derivative of y hat with respect to wij? Well, to do that, we first have to rewrite this y hat in terms of how it basically is produced. So derivative of y hat with respect to this particular formula is basically, what is y hat I? This is actually the sigmoid of j varies from 1 to 512. These are our, that's the size of this w. And then we have this w I j into f j. Remember, this f was a long thin vector of 512 entries, and that number plus the bias at this particular location. So that's the sigmoid of that. Now the derivative of sigmoid always is can be computed in this particular way, that is y hat I into 1 minus y hat I into the derivative of this particular term with respect to ij, and here you can notice that this particular term becomes simply fj. So now the derivative, I have just written this, I should have written this particular box in place of this. So if I rewrite in the next slide the derivative of L with respect to a particular entry ij is basically y hat I minus yi into y hat I into 1 minus y hat I into f of j, and all these things, they are known, and that's how you can compute the derivatives with respect to every weight, actually with respect to all these weights associated with this. But that was an easy part, because the reason that that's an easy part is because that basically is ordinary in neural networks, how to compute these derivatives in plain neural networks. The harder part, however, is for convolutional layers. But we will, by deploying these kind of chain rules, we will be progressively moving towards convolutional layers as well. So that's the derivative with respect to wij. Now let's compute the derivative of the loss function. Remember, we always have to compute the derivative of the loss function. So that's our loss function. Let's compute the derivative of the loss function with respect to a particular entry in J. Let's say that, just to apply a chain rule. That if you see, if you, for example, see how this particular entry is impacting our loss function, it can impact our loss function through this neuron, or through this neuron, or through this neuron, or through this neuron, or through this neuron. That means if there are multiple paths towards the loss, the derivative actually, the derivative with respect to that entry actually has a summation in that. So OR just is reduced with summation. So we have I varies from 1 to 5 in this particular case. The derivative of the loss, how basically how this f impacts basically our y hat, and then how y hat actually impacts our loss. That's the same thing as we saw earlier. So that's again a chain rule to compute the derivative with respect to f. You might be thinking f is not a parameter, why we are computing derivative with respect to it? Well, y hat is also not a parameter. We will compute this differentiation just to backpropagate to compute the actual parameters. So you can think of this as, yes, that is true, f is not a parameter, the vector f does not contain parameters, but differentiation with respect to that will lead to the differentiation of the parameters that we eventually need. So this can turn out to be, if you just focus on it with respect to fj, this again turns out to be kind of thing as you see in the previous case. This thing is as if this, and the differentiation of this with respect to fj pulls out this thing out. So in that case, we actually come up with the result, which is y hat summation y hat I minus y I, that thing, and then we again have y hat I into 1 minus y hat I, that's the same story as before, into wij, just you can see the previous derivation. There we were differentiating with respect to w, now we are differentiating with respect to fj, and that's what it brings. And that's the derivative with respect to fj. So now all the derivatives with respect to fj, they are available. Now the next part is most interesting. This f was actually the flattening out of our s. So if we reshape this again into 16 by 16, that's all the derivatives. If we reshape them into 16 by 16, we actually now have derivatives of s1 and s2. So the reshaping actually brings the derivative of L with respect to s1 and the derivative of L with respect to s2. And further, because the max pooling brings it from C1, I'm just focusing on C1. So for example, the very first entry here is actually the max of the 4 entries here. So only the maximum entry of this box is contributing towards the loss, because the rest of the entries, they were chopped out. That means this derivative will propagate exactly back at the place where the maximum entry is, and the rest of the entries, they will become 0. That means the derivative of loss with respect to the derivative of Cij is already computed once the derivative with respect to f has been computed, because that is the derivative with respect to s1, and because s is the max pooled variant of c1, all these derivatives, all these values that are not maximum, they cannot contribute to the loss, so hence they have no gradients, and the only gradient value is the value where the maximum is, and that actually propagates back to as it is from this particular value. Now once we have these derivatives computed for C1 and C2 in the similar fashion, now we are really ready to actually compute the derivatives with respect to K1 and K2 and stuff like so. And that I will now be going over a little bit quickly. So the derivative with respect to, if you remember the C1, let's say Ij entry, if you remember by the definition, that entry basically is ReLU of summation u varies from -2 to 2, v varies from -2 to 2, and then we have this k1, for example, uv into image I minus u, and v j minus v. Obviously, this thing plus bias, let me call it b1. If you see that, then differentiating L with respect to this particular parameter, again by the chain rule, differentiation, computing the impact of this parameter on loss, K1 UV by chain rule is the same as having a summation I varies from 1 to 32 because our image is 32, j varies from 1 to 32, and this becomes basically the impact of impact on loss of this particular entry Cij into how basically Cij is impacted by this quantity. And now you already have computed this particular part that is there. You already have computed. All you're left with is to compute this particular part. And now you can see if you differentiate this with respect to this part, this actually goes away. That's a linear function in K. And the only result that resides is I minus U and J minus V, and B is also gone out. So that's the derivative with respect to the parameters. And that's it. Now we can compute the derivative with respect to B1 in the similar fashion and the other biases with the similar fashion as well. So although I went through really quickly in this video because of the shortage of time, I should cover all these things in a bit more detail, but that requires a lot of time. Although in our full course on AI sciences, we actually have discussed each and everything in details and actually have implemented backpropagation completely in NumPy for this particular example. But here I have sketched certain things that will lead you toward better understanding of how the backpropagation works in convolutional neural networks. So I also recommend you to go to AI Sciences and enroll our full course on convolutional neural networks, where we explain all these things in detail, in step-by-step, as well as we have live coding in NumPy as well. So if you basically like our content, please press the like button, subscribe our channel, and share our content with your fellows. Hope to see you next time.